Thank you, Enyo. Good morning, everybody. Yeah, so I'm going to talk about this tension, which is now 6.4 sigma tension. That's when you compare the measurement of H naught, assuming lambda CDM, with the most recent combination of CMB data, including the latest ACT and SPT release, with the most recent measurement of H naught from shoes, which is from a bit more than 1 year ago. And so this is really not just a tension between Planck and shoes or CMB and shoes. It's a more general thing. It appears when you look at when you compare different types of measurement of H naught. For instance, the tension would still be there, although with maybe a smaller significance, if you would replace shoes by other measurement of H naught from TRGB, from the CCHP experiment, from strong lensing, from other calibrators like the comma distance. And it would subsist if you would replace CMB experiment by a determination of H naught from, for instance, combination of BBN and BAO data. So it's a general thing. It's very worrisome. So the big question is this systematics in the data, or does it require new physics? And of course, I'm not able to answer this question today. Nobody is. It's a very delicate issue. There is no trivial answer. The only thing I can do is to try to give a fair summary of what is going on and what people tend to think. So first, you might be under the impression that last summer, there was an indication that the tension would disappear when CCHP, the Carnegie Chicago experiment, released a paper in which they say that they were comparing 3 methods to calibrate supernova luminosity with different calibrators, so different standard candles, which are Cepheids and JAGB and TRGB, which are quantities you infer from the color luminosity diagram of stars. And in a paper from the last summer, Friedman et al. Were advertising that these 3 different methods give 3 different results, with Cepheids giving the largest H naught and JHGB the lowest one. And at the beginning, people were under the impression that this was a crucial piece of information showing that these different calibrators are contaminated by systematics because they don't even agree with each other, which would be really the proof that there would be some unknown systematics. And after all, if Cepheids would be systematic dominated and JGB would bring the right answer, then from a plot like this, you would say, okay, the tension is on the edge of completely disappearing. But this is really not the case, because after this paper, there have been some intense work, both from the shoes and the CCHP team, to better understand the origin of this shift. And the origin of this shift is actually not a contradiction between the different calibrators, Cepheids, JGB, TRGB. And one way to be sure of it is to look at special host galaxies, where in the same galaxy, you can see at least 2, or if not 3, of such, you can use 2 or 3 of these calibration methods. And when this is the case, the different determination of the distance from Cepheids, JGB, or TRGB always perfectly agrees. Instead, it was understood that the shift between the 3 results is due to something completely different. It's a fact that in this particular analysis, or in the first version of this analysis, the population of host galaxies that was used to calibrate with one of the 3 calibrators were not representative sample and could easily be shown to be biased with respect to each other. In other words, this was not a discrepancy due to the physics of the calibrators, but to selection effects. And there was an effort to compensate for this or to cancel these selection effects. So there were many publications from the shoes team and collaborators of shoes where they tried to use their own GAGB or TRGB calibrators, and they found that all methods are consistent with each other, but never as precise as what they get with Cepheids. And also, in the published version of the CCHP paper, the plot that I is no longer there, because they acknowledged and they agreed that there were selection effects. And instead, the focus of the paper is more on demonstrating that when you try to calibrate supernovae or the standardized magnitude of supernovae from GAGB or TRGB, or even Cepheids, you do get consistent answer. So this evidence for a problem went away in some sense. So the problem is still there. And as you have seen in the previous plot, this one, when the SHOES collaboration tries to use JGB or TRGB from the James Webb Telescope in order to calibrate supernovae, instead of their traditional Cepheid method, they get a very wide error bar. So there were publications by SHOES recently where they add TRGB calibrated calibration on top of Cepheid calibration. It does not change their result significantly because their result is always dominated by Cepheids. But what is interesting is that in August, there was a release by a completely independent group. This is not SHOES, this is not CCHP, it's a group where the first author is Max Newman from Rutgers University. And this group have a measurement of H0 based only on the TRGB calibrator. It's completely independent. And they find, again, a very large H0 with an error bar, which is 3 times bigger than the SHOES error bar, but which is still not bad. And so from TRGB only, it seems you do have a Hubble tension, again, which is quite significant. On the side of the SHOES collaboration, they have not really improved their measurement till 2024, but they have cleaned the analysis of possible sources of systematics. And in particular, there is a worrisome systematic in this business, which is called crowding. So when you look at a Cepheid, you want to measure its period in order to know the absolute luminosity. But of course, you want also to measure the mean or the average apparent luminosity in order to get the distance. And this second measurement is delicate because in a pixel of your data, you see a variation of luminosity in a big pixel or in a few pixels, and you are never sure that the luminosity you measure comes from one Cepheid alone or one Cepheid plus light from another star, which is almost aligned with a Cepheid. This effect is called crowding. It could lead to a wrong estimate of the apparent luminosity of supernova and thus a wrong estimate of their distance. And for some time, people believe that this could be the systematic that would be at the origin of the Hubble tension. Then the SHOES and CCHP collaboration had arguments to show that it should be a small effect and to correct for it to some extent. But a lot of progress has been done with the JWST telescope for several reasons. First, now when you look at the same Cepheid, for instance, at the center of this pixel, there is the same Cepheid seen by HST and GWST. And due to the much better angular resolution, it's much easier now to isolate the light coming from really a single object and be sure it's not contaminated by another one. And there was another argument published recently by the SHOES team, because they were lucky to observe a very special galaxies which has a tidal host. So this is the main galaxy, this is a tidal host. And we know that they are really close to each other. So from our point of view, essentially at the same distance from each other. This galaxy is a typical type of galaxies that is usually being used in order to calibrate supernovae from Cepheids. So it's a typical host galaxy with Cepheids. Because it's old, it has a big background of stars. And when you zoom on a region of it, you see that it's very dense. And there could be potentially some crowding effect. But in the tidal host, it's a much younger object with much less background. And it's clear that the Cepheids that you observe in this object cannot be contaminated by crowding. The image you get from Cepheids in this object, which is here on the right, is very pure, and there are no other stars close to the line of sight of the Cepheids. And what the SHOES team showed is that when you do a calibration of the Cepheids from either of the two objects, you get the same result, which is a proof that crowding was not really an issue and a serious source of systematics. And in particular, they get a lot of data from JWST, which is completely crowding safe. So they have not changed their measurement and their error bar, but they have just ruled out in a convincing way crowding as a possible source of systematics. So this is a summary, and if you want if you are not specialists like me, and you want a very nice pedagogical update on the observational status, you can watch a really nice seminar that I saw last week by Louise Broyval, and it was given in the context of the Cosmoverse webinars, and it has been posted on YouTube yesterday. It's 45 minutes, and it's very complete and very easy to follow. Yeah. They have a lower central value and a large error bar, and they no longer claim this shift between different calibrators. So they agree with everybody. They agree with the large value and the low value. They have a central value which is around 70, and they are no longer claiming a central value of 68 with JGB, because this was based on a non-representative sample, and when you correct for this, the central value moves around 70 again. Yeah, sure. Okay, so on top of this, okay, we have a multiplication of tensions in cosmology, and the situation is really becoming embarrassing. So we have talked for a long time about the S8 tension on the amplitude of the power spectrum from weak lensing. This tends to be slowly going away. You know that the last analysis of Keats, a Keats legacy paper, claims no significant tension. Theirs is still at 2-ish sigma tension level, no more. So this is no longer a big concern. People were worried for a while about this lensing anomaly in Planck data, meaning that the temperature spectrum essentially appeared as so smooth that there seemed to be like some spurious source of lensing of the data. This has gone away. It's less clear with the last Planck data analysis by various groups, and ACT and SPT do not find this. So this is essentially gone. But we have this other tension that came from the recent DAISY measurements, which in the lambda CDM model, you would interpret primarily as a tension on big omega m. That you should think in this context not as a parameter for the density of matter, but really it's omega m equal 1 minus omega lambda. It's a parameter that tells you when you switch from matter domination to lambda domination. And the possible solution for this, as you know, is dynamical dark energy. And actually, if you don't assume dynamical dark energy, but you are convinced that the DAISY results are fully correct with correct error bars, then you anyway get a problem with the neutrino mass, because the upper bound that you get for the neutrino mass is ruling out the minimal value of neutrino mass from neutrino oscillation at the 2-3 sigma level. So there is something odd going on here. Yeah. Yeah. Yeah, because the tension on omega m will give you a tension on S8, because S8 contains omega m. Yeah. So one possibility is that we get a multiplication of tension, because there is a general trend in the astrophysical community to underestimate errors, and the errors from both sides should be larger in reality. Or maybe these tensions are different hints of the same new physics and the need to go to another standard cosmological model. And the big question at the moment is to find out which of the two is correct. And now I talked a bit about observations. Now I will go to the theoretical side and say, okay, let's assume there are no unknown systematics. We take all the data set as they are, and we wonder if we can explain this tension by a change in the cosmology. What is the price we need to pay? Are there working models? If they are they elegant or ad hoc and fine-tuned? Okay, you can guess what will be the answer. But we are going to go through it and summarize the situation. Okay, so We measure standard rulers and standard candle distances, and the Hubble tension is about a disagreement between the two, essentially. So to know the distance to redshift relation, you use a standard relation for a Friedman universe. And then if you have computed this, in principle, the angular diameter distance is immediately given because we have this distance duality relation, which is very, very general. To break it, you would need some very special theories of gravities. I will come back to it. Or some, if you want to break it at a fundamental level, you would do it through